Hello everybody, hello there ROS developers, and welcome to another open class. We are today in open class number 182. Hello everybody. First of all, let me please know if the sound is good in here in the chat, so that I can be sure that you can hear me properly. Sound is good, is saying Ricardo. Andreas, Jan, all right, excellent. Then, so first of all, let me apologize for having to cancel yesterday's class. We had some technical issues, and finally we had to cancel it, but we are going to compensate you by providing an amazing class today. So I'm sure that you're going to enjoy it. We are going to be working with a simulated robot. We are going to be working also in the second part of the class with a real robot. So we are going to have double robot session today, both simulated and with real robots. And we are going to be working with a super cool robot, which is the Limo robot. You will know it in a moment when we start the class. And we are going to be doing very cool stuff also. We will be creating a wandering behavior using potential fields. So stay tuned, because I'm sure that you are going to enjoy a lot this class. And without further ado, let's get started with the class. So let me switch already here to my computer screen right now. Let me do that in a moment. There we go. 1 second, there we go. Okay. I think there is some kind of issue. Let me try to fix it here. There we go. All right. So, let me, of course, get to the page so that I can start seeing your messages and everything. Let's go there. Here we are. Okay. Messages. Then, as always, I don't know if you are new to open classes, if this is your first class. If not, there are some names that I am reading here in the chat that ring a bell for sure. I know that this is not your first class, but in case there is somebody new, which we always welcome new people to our open classes, know that these classes are not meant to be followed passively. Okay, so we want our attendants, to our students in the class, to be actively part of the class. Yeah. So in order to do that, what we do is to share with you a complete project. All right. So in order to get this project, this is the very first thing that you should do. What you have to do is to click here on the button that you have right above the chat, which says fork and open the class project. Yeah, this is going to provide you with a copy of the project that we are going to be working with today. So I'm going to click here myself to get my own copy of today's project. And so please, all of you, go ahead and click there. And then, as always, also I'm going to move here my streaming area. This, you are going to also have it here with so that you can follow the video and you can write in the chat meanwhile you are working. I'm going to move this away so that I have some more space here to work. There we go. Here to work. Not here, sorry. There we go. Let me put the chat here. Need to mute this. There we go. Okay, so we have here a new student who is Subhajit. So I hope that you enjoy the class, Subhajit. All right, then, so let me close this. There we go. Okay, then I have here a bunch of things opened, but when you get your project open, what you are going to see is something like this, yeah? The very first thing that you should see is the notebook of the class. Yeah, so in this notebook you are going to find all the things that we are going to be covering or following during today's class. Yeah, so it's a guide for the class with some theoretical concepts, commands that you are going to have to execute yourself, images, pieces of code, etc. Yeah, I'm going to be following this notebook for today's class. So in case that you want to review something, you are going to find everything here. All right. Then, yeah, so before actually getting started, let me wait until everybody has their ROSject open. So can you guys confirm here in the chat if you have been able to open the ROSject successfully? It has loaded already, still loading. What is the status so far? ROSject opened, says here Ricardo. Done, opened successfully, loaded and ready. Loaded, opened. Okay, excellent. Then we are ready to get started. So today we are going to do a class in association, in collaboration with Agile X Robotics. Yeah, I don't know if you are familiar with Agile X, but it's a company that they build robots, and one of their latest products, or not latest, but coolest products, is the Limo robot. It's this guy that we have here. Super cool robot that provides sensor data via laser, via a camera. It has an RGB camera, so you can also get point cloud information. It has several steering modes. You can see here in the image the omnidirectional steering mode. You can also work with it in a regular differential mode, but it also provides the possibility to work in Ackermann mode. So it has a screen here in the back. We will see more about it later, but super cool robot. And we have one here in our offices that we are going to be also working with, connecting to later. But before that, we are going to start working with a simulated version of the robot. Yeah, always we recommend to start working and testing things in simulated environments. Yeah, because if something goes wrong in the simulation, you just have to close the simulation and restart it, right? If something goes wrong in the real environment, then some things, real things, might get damaged, or the robot could even break, whatever. So always let's start working with simulations, all right? Then the very first thing that we are going to do is to launch the simulation of this robot in a cool environment that you are going to see in a moment. So in order to start the simulation, we are going to run this command here that you are going to find here in the notebook. Yeah, but in order to execute this command, you need a terminal, a shell, right? So in order to open a shell, what you have to do is to come here to the bottom section of the ROSject, and you are going to find several buttons here. At the first one here, you are going to see it says Web Shell. So this is the one we are looking for. If you click here, this is going to open a new terminal. This is a regular Linux terminal where you can type commands. Okay. And then in order to execute this command, all you have to do is to copy it. You can copy it directly like this with the button, or just selecting and copying with Ctrl+C, whatever, however you prefer. Yeah, but let's copy the command here to launch the simulation and paste it here into the terminal, and then we press enter in order to execute it. All right, and we are going to start seeing a bunch of things here in the terminal, as you can see. And then this is going to open two things. First of all, it's going to open an ROS window, like you can see here, and also a gazebo window, like you can see here. Okay, let me put them here together. Okay, this is ROS and this is gazebo. Okay, these are different things. Yeah, do you guys know what is the difference between ROS and gazebo? Yes, no? Okay. Ricardo says that my simulation crashed. I think mine also, so I'm going to address this in a second. Let me see. I know gazebo, not ROS. Yeah, Jeff says that yes, he knows. Puya says gazebo is a physical simulator, but ROS is a mere visualizer. Yes, exactly. That's the right answer, Puya. So Gazebo is a physics simulator, and RVs is a tool that you can use in order to visualize things, like for instance, sensor data. Yeah. Then, in some cases, you might have something like this. You see that my Gazebo it's not showing anything, and also here in RVs, I cannot see anything. Here, I should be seeing some information, like I can see in this image here with the lasers. Yeah, these red things are the laser readings, but I cannot see any of these. Yeah, this means that my simulation has crashed. So in case that you are in the same scenario, all you have to do is to come to the terminal where you executed the command, press Ctrl+C, like this, to stop the command, and then just execute it again. Yeah? So you terminate the command and you execute it again. Sometimes Gazebo has problems when being launched, especially the first time that you execute it. There are some timeouts there that sometimes fail, and the Gazebo simulator fails to load. So let's just execute it again, and the second time it should work properly. So let's see. Okay, so now, as you can see in RVs, I have the red things, which means that I am visualizing in RVs, sorry, the data from the laser of the robot. Right? And from where I am capturing this laser data? Well, in this case, from the simulation that I have right here in the right side. All right? Then this is the simulator. This is the physics simulator here, Gazebo. And in this case, I'm going to zoom in a moment here. Here, I have the robot. This is the simulated version of the Limo robot. Okay, we can see it here. And in this case, we have a simulated environment, which, as you can see, it's an office environment. Yeah, so we have here an office with some computers, tables, chairs. Yeah, typical office that you can find in many companies. So yeah, this is the simulated environment that we are going to be working with. All right, very cool simulation, by the way. Let me get back here to the view, and I'm going to unzoom a little bit so we can get a better view of the office. Not so much, maybe. There we go. Okay. Some printers also. Yeah. Okay. Yep. So far so good. Is everybody here? Have you been able to launch the simulation properly? And you can visualize the laser and everything in RVs? Yes? No? My Gazebo screen says, okay, yeah, this is Ctrl+C and launch it again, exactly. Try again. Okay, it worked now. Yes. Jan is asking, how to extend RV's window? Good question. So, basically, if you have it small, you have two options. So you can double click here in the top bar of RVs, or you can also click in the maximize button. Okay, so this is a window, and it has a maximize button here also, which is going to make it bigger. Okay, and then outside that, this is just a window that you can make as big as you want and move along the environment like this. Okay, everything working, everything is right. RVs and Gazebo look okay, but I can't find the robot. Yes, robot is a bit tiny, but it's here. Okay, if you move around the office, you are going to eventually see it. Yes, I am noting this. So so yeah, let's hope that that I don't get trolled with this, with everybody mentioning my name, because I'm going to get crazy. So let's try to keep things as calm as possible. All right? Okay, very well. All right, so now we have our robot that we can start working with in the simulated environment. And there we go again. So let's do something with our robot, right? So very cool. We have a robot in a very cool environment. But let's now do something with this robot, right? So what are we going to do? What we are going to do for today's class is that we are going to create a wandering behavior for this robot. Do you know what a wandering behavior is? Does somebody know? First time that you hear it? Wandering behavior. Let me write it here. Jan says no. Subhajit says autonomous movement. That's too general. Autonomous movement can mean a lot of things. So it is related with that, but yeah. So basically, a wandering behavior is, Puya says, following along the walls. Not exactly. Atal says just roaming. That's more accurate, yes. So basically, a wandering behavior is that the robot is going to keep moving continuously while avoiding obstacles. Yeah? It's going to keep moving along the environment, in this case the office, continuously without stopping, and while avoiding obstacles, okay? And how? Okay, so moving the robot continuously is pretty easy. I mean, you just have to send velocity messages to the controller of the wheels, right? And then the robot is going to keep moving. The tricky thing here is that it has to avoid obstacles, right? So how are we going to implement this part of avoiding obstacles? Well, for this, we are going to use an approach which is known as potential fields. Okay? Does somebody know about this potential fields approach? Are you familiar with it or not at all? This is a concept which is pretty well known in robotics. Francisco says yes. Jan, not at all. Andreas says yes also. Not at all. Okay, so we have a bit of everything, 50-50. That's good. So for the ones that already know, they are going to be able to get to practice with this. And for the ones who have no idea, then they are going to learn something new. Very interesting today. Yeah? So what is a potential field? And a potential field is a method to navigate a robot in an environment, first of all, and it is based on the concept of potential energy. Yeah, this probably most of you know what potential energy is. This is done in the school when you do physics, right? Then the robot is attracted to the goal and repelled by the obstacles. Right? This is very important. The robot is attracted to the goal and repelled by the obstacles. Okay? Then the final potential field is going to be the sum of the potential energy of the goal and the obstacles. Okay? Here we have a GIF that we can see. This is the starting point where the robot is currently. This is the goal, and these are some obstacles on the way. So a potential field would result in a trajectory which looks something like this. Yeah? It goes towards the goal, but if it finds any obstacle in the way, it's going to avoid them. But this can be easily seen here. Yeah? So this attraction and repulsion that we were talking a moment ago, this can be better seen as vectors. Yeah? So imagine that we have our robot in the starting point, here in the left side, and here at the right side we have the goal point, or the destination point. Yeah? Then, as you can see, the robot is going to feel attracted. You can see all the arrows which are pointing towards the goal, which is here. Yeah? All these vectors represent the attraction that the robot is feeling towards the goal. Yeah? However, if there is an obstacle in the environment, this obstacle is going to provide vectors which repel the robot from going towards the obstacle. Yeah, you can see that in this case, all the vectors go from the obstacle outside. Yeah, so the robot is going to feel attracted to go here, but when it reaches this zone, it's going to be repelled by the repulsive force of the obstacle. So the ending trajectory, the ending vector is going to be something around this trajectory. Yeah? Once the obstacle is passed, then again, the attraction forces towards the goal are going to be winning, so the robot is going to reach the goal. Yeah? Then, okay, here we can see an example of initial position, goal position with an obstacle, yeah? But how can this be translated to a wandering behavior? Well, it's very simple. What you do is that you set a fixed goal. A fixed goal. So the robot is going to have always the same goal. And what is going to be this goal? Move forward, yeah? So just move forward. This is going to be the goal that the robot is going to have always, yeah? And then whenever the robot finds obstacles on its way, it's going to avoid them using these repulsive vectors. Yeah? Does it make sense? Do you get the concept of these potential fields? Does it make sense? Subhajit says no. I don't know if he says, yes, okay. Yes, okay. So I can see that you understand the concept. Okay. In any case, this is very theoretical, right? Francisco says perfect, but this method can show problems if it reaches a local yes. So yeah, exactly. So there are some local minimas and some things where this method can have some problems, but we are not going to focus on all that, okay? So what we are going to create is just a basic, let's say basic wandering behavior, okay? That it can more or less do the job, okay? We are not going to be focusing on having something super robust, yeah? Or getting too much into details, all right? Then, okay, so this looks very nice in the theory, but let's put this into practice, okay? This is what we are going to do now. So let's create a ROS2 program that implements all this theory into something practical that the robot can do. So for this, we are going to altogether start by creating here a new package, yeah? I am in part 2 of the notebook right now. Create the ROS2 wandering program, okay? So let's go back to the terminal, and here you are going to, this is where the simulation is running, okay? You can see many messages being printed here, don't worry. But this, you are going to leave it running, okay? If you close this, the simulation is going to die. We don't want that because we want to work and play a little bit with the simulation, right? So what we are going to do is just to open another terminal, yeah? And we can do this by clicking here in the plus icon that we have here. If I click here, this is going to open another terminal, yeah? You can even rename the terminals if you want to know where you have everything. So here I have the simulation, okay? And then in this new terminal, I'm going to create my package, yeah? So now in this second terminal, I'm going to create the package with the ROS2 package create, but very important, whenever you create a new ROS2 package, you have to be in the source folder of the ROS2 workspace, okay? These are basic ROS2 concepts. Then let's go to the SRC folder of our ROS2 workspace, and then here we are going to create a package. Okay? There we go, ROS2 package create. The name of the package is Limo nav. It has some dependencies, as you can see here, and it is a Python-based package, yeah? Then, at this point, if I run an ls here, I'm going to see my package, which has been created here, okay? But better than this, what we are going to do is to open a code editor, yeah? Because we are going to be creating code now, and for working with code, it's always better to have a code editor, right? It's much more practical. and user-friendly. So for this, what we are going to do is to go here to the bottom icons, and we are going to click on the second one, which says Code Editor. Yeah? If you click here, this is going to open a code editor. There we go. See? And now in this code editor, basically you have access with a graphical interface to all the folders, workspaces, files that are contained inside this project. Yeah? Now, in this case, we are going to be working with the ROS2 workspace, so we can open here the ROS2 workspace, and if we go inside the SRC folder, we are going to find our new package, which is the Limo nav. Okay, here you have some other packages which are related to the simulation. Yeah, but this is the package. This Limo nav, Limo_nav, is the package that we have just created, right? So, what else? Now what we are going to do is to create a new Python script and put it inside our package. Yeah, we are going to name this Python script as wandering.py. Okay, so how can you do this? Very easy. You can come here to the Limo nav, package, and then open the second Limo_nav folder. Yeah? So we have Limo_nav and Limo_nav. When you open the second one, you are going to see that it already has an init.py file here. So in this second one, you can right-click and select the new file option. And then here you can write the name of the file, wandering.py. There we go. As you can see, a new Python script has been created here, and right now it's empty, as you can see, right? We have just created it, so it's empty. Yeah. Then what we are going to do now is to populate it, is to put the code into the Python script, and the code you have it right here in the notebook. Okay. So I'm going to select from here the code. I'm going to select everything until the end, which is here, okay, in the main, and then Control-C, or right-click and copy, whatever you prefer, and then here you can paste it with Control-V or right-click and paste. There we go. Okay, so now here we have the code. We can, inside our wandering.py script, we have all the code for the wandering behavior that we are going to be reviewing in a moment. Okay? Yeah? So far so good. Are we following? Can we compare this to an nav2 behavior plugin? Not exactly. I wouldn't say so, Gilbert. Yeah, so if you miss any of the steps, you have everything step by step here in the notebook, okay? So you have everything here. Go inside SRC, create the package, create the new file, add the code to the file, okay? Then what you should have now is the code here, your package, Limonav, with the wandering.py script here with all the code, okay? Then there's one more thing that we need to do in terms of code. Last thing that we need to do is to update the setup.py file of our package in order to generate an executable from this program. Okay, so let me do this right now. So here you have to come again to your package and open the setup.py file, okay? And then here inside the entry points console scripts, you have to add this line here, or you can also just copy everything and paste it, whatever you prefer, okay? You can copy everything and replace the contents, or just add here this line inside the entry points console scripts, whatever you prefer. Okay, I'm going to add only this line here. It's right here, yeah? Inside entry points console scripts, I'm going to paste this, okay? So what this is going to do is to generate an executable file, which is going to be named wandering, from the Python script that I have created here, okay? So that we are going to be able to run it with ROS2. Okay? Now, last step to have the package ready is to compile. Okay? But before we compile our code, we are going to explain what's going on here. Okay? Because there's a bunch of code here, many things. So I'm going to explain. I'm not going to go super into detail, okay? Because basically I don't have the time. But everything that we are doing here is explained in our ROS2 basics courses, okay? I will show it later again, but here at the bottom of the notebook, I have left a link to our ROS2 basics in 5 days course, where you get to learn all the basic stuff related to ROS2, okay? Then, what do we have here? Okay, let's focus on the code, and let's focus on the most important or relevant parts of this code, right? So at the beginning, we have a bunch of lines in order to import some libraries, module, messages into our program, so that we are going to be using them, right? Then here we are creating our class, which is named potential field. And then here we are creating a couple of callback groups, okay? These callback groups are used to better handle callback executions in our programs, yeah? For when we have multiple callbacks. Then what do we have here? Here we are defining some publishers, yeah? Publishers that we are going to be using for different things. First one, we have the publisher for the command belt topic. Does somebody know what this publisher is used for? When we publish into the command belt topic, what are we doing? Somebody know? The IDE shows many... okay, yeah. I see that some of you are having problems here with the... Yeah. Try to avoid using these, especially for codes. For commands and everything works okay, but when copying code, using this tool maybe sometimes gives problems, okay? So for the code, only for the code, just select it and copy it, okay? Jan says, control velocity, moving the robot. Yeah, exactly. Yeah, so when we publish into the command belt topic, what we do is to move the robot, yeah? So here we have a bunch of publishers. Here we have 3 publishers to publish the vectors of our algorithm, yeah? We are going to be publishing the attraction vector, repulsion vector, and the final resulting vector, okay? So that we can visualize this in RVs and get a better understanding of what is happening, yeah? Then here we have a subscriber. We are creating a subscriber to get the laser data, right? Here we are declaring a timer where we are going to place our main control loop, okay? The main control loop is going to be executed in a timer, using a timer here, periodically, all right? Then finally, at the end of the constructor, here we are declaring, initializing the attraction and the repulsion vectors, okay? Then, let's move down here. Let's skip for now the controller, okay? I'm going to go to the next method, which is the create vector pose method, okay? This vector is just a helper method that we use in order to create a pose stamped vector, okay? We are creating it in a pose stamped, with a pose stamped, so that we can visualize it in RVs, yeah? Later, when we execute it, you are going to see, let me show it to you very quickly here in the notebook, you will see that in RVs you can visualize these vectors that represent the different vectors, right? Then in order to be able to visualize this, we have to create a pose stamped, okay? So this is what we are doing here. We create a vector using a pose stamped interface from ROS2, okay? Then here we have the laser callback, yeah? This is the method that is going to be executed every time new laser data arrives to the robot, yeah? And then here what we are doing basically is to analyze this laser data that is coming, and then with that data we create the repulsion vector, yeah? So the laser data, right, is the one that is going to detect the obstacles, right? So with this data, what I'm going to create is the repulsion vector. Yeah? So in this case, you have it here, yeah? But the green vector represents the attraction vector. The yellow vector represents the repulsion vector. And the red vector represents the final vector, yeah? Then the green vector, which is the attraction vector, is always going to be in the forward direction of the robot, right? Because our goal is always move forward, yeah? So the attraction vector is always going to be the same. It's going to be pointing forward, all right? And then, based on the laser data, we have to generate the repulsion vector, which is this yellow one, yeah? In this example, for instance, we have some obstacles here, which are quite close to the robot, yeah? Therefore, the repulsion vector is telling the robot to go away from the obstacle, yeah? Do you understand this? So and this is basically what we are doing right here. We are analyzing all the readings and generating this vector, okay? In this case, we are actually not analyzing all the readings, but only the ones which are between 8 centimeters and 60 centimeters from the robot, yeah? So we are filtering out readings, laser readings that are far away of the robot. In this case, that are more than 60 centimeters away from the robot, yeah? And also the ones which are too close to the robot, we are filtering them to eliminate noise that can come from the robot detecting itself and things like this, yeah? Do you understand this? What I am explaining here with the attraction vector, the repulsion vector, how the repulsion vector is being generated from the laser data? Yeah? Does it make sense? Yes. Reinato is asking, excuse me, I want to ask, what is the publisher of scan topic that the laser scan subscribe from it? I don't understand your question. The laser scan, this is, the scanner is not a publisher, it's a subscriber, okay? This is a subscriber. These are publishers, so you publish data into the topic, and this is a subscriber for the scan. So you read information from a topic, okay? What is the red vector? Is asking Puya. Good question. So the red vector, we say that the green one is the attraction, the yellow one is the repulsion, and the red vector is the final vector, okay? So this is the result of combining or adding the attraction with the repulsion. So this is going to be the final behavior of the robot, yeah? This means that in this scenario, the robot is going to try to follow the red vector, the final vector, okay? Yeah, Subhashit, kind of. Okay, let's continue, yeah? So we have the scan callback where we are computing here, we are processing the laser data, and then we compute, yeah, we create the repulsion vector, all right? And then let's go back to the controller, yeah? So in the controller, what we do is to compute the final vector. This red vector that you were asking, what is this? Okay, so this is the one that we are going to actually use to move the robot, yeah? And here is where we are computing the final vector. Yeah, as you can see, by adding the attraction vector with the repulsion vector, all right? Then here we are publishing these vectors so that we can visualize them in RVs, yeah? And then here what we are doing is, based on our final vector, we compute the linear and angular velocities, okay? So based on this vector, on the final vector, which is the one that I want to follow, what I need to do is to convert this information into actual velocities for the robot, yeah? So that the robot can try to follow the direction of the final vector, right? Then here we are computing, we are exactly doing this. We are computing the linear velocity and the angular velocity, right? And then we convert these velocities to twist, which is what the robots understand, yeah? So this is a linear velocity in the x-axis, and this is an angular velocity in the z-axis, okay? Yeah, and here we are just filtering, lowering a little bit the speeds, okay? Because otherwise the robot would move too fast. Yeah? So this is basically a basic explanation of this algorithm, right? There are some mathematical things going on here, yeah, like computing arc tangent, yeah, modules of vectors, but I don't want to get too much into detail here. So what is important that you get from here, I think, is that you get a general idea of what's going on in the code, yeah, more than understanding exactly all the mathematical equations, right? Yeah. So does it make sense? Yeah, do you understand the different parts of the code? Well, finally, I was missing the main function, but basically the main function, what we do is to create a multi-thread executor, and then we basically a multi-threaded so that we can have callbacks running in parallel, and then we just spin this executor forever until somebody stops the program. Yeah, for instance, by pressing Ctrl+C. Yeah. Does it make sense, more or less? Do you get a general idea of the program, the different methods of the program, what is going on? Yeah? No? Any questions? Jan says yes. Okay, so yes, and it works. Okay, well, that is what you say, Andreas. I have not tested the code yet, so I cannot say that it works. So let me do that, all right? So right now what I'm going to do is to test if this works. Yeah, so the code is very nice, very well explained, Alberto, but does this work? Okay, so this is what we are going to check right now. Then let's go for that. So let's, in order to test it, of course, we have to build the code, and here you have the commands to do it. Yeah. So let me go to the terminal here and execute this. So in order to build, very important that you go to the source of the workspace. Yeah, not in the SRC, but you have to go here. Yeah, to the ROS2 underscore workspace folder in order to build. Then now we build with the callcom build command. So now we are building and generating the executable, yeah, from this Python script. And then we are going to end up sourcing our workspace. There we go. And now the time of the truth has come, okay? Well, in case that for some reason you have stopped RVs here, you can relaunch it very easily with RVs2, okay? If you don't, then just leave it running, okay? And now this is the command to execute our program. ROS2 run, the name of the package and the name of the executable, which is wandering, okay? So what I'm going to do here is to allocate my window so that we can see, we can have a proper view. So let me put RVs here so that we can see what's going on, right? Let me put the simulation down here, maybe. Actually, I'm going to put the simulation here in big. And the terminal, I'm going to put it here, smaller. Let me put it here. There we go. So here we can more or less have a view at everything, right? What is going on? You have RVs here, simulation. Okay, so let's execute the code and let's see what happens. let me copy the command directly from here, execute it, and let's see. So the robot should, okay, so here we can see the attraction vector, the green one, the repulsion vector, which is the yellow one, and the, let me zoom, and the final vector, which is the red one, yeah? So as you can see, the robot tries to go for, so the attraction vector is always pointing in the forward direction of the robot, yeah? And then whenever there are obstacles detected, the repulsion vector tells the robot to move away from them. Okay? So now the robot keeps moving forward, as you can see. Okay, now these particles are being detected, so the repulsion vector says, hey, move away from here. And then the final vector tries to make the robot rotate also. There we go. There you can see how it keeps moving around while avoiding obstacles. Okay? Yeah? Now it's moving towards this table, but whenever this is detected, the repulsion vector is going to tell the robot to move away from it, as you can see. Okay? And we could leave this program running forever, and the robot would keep wandering around the office while avoiding obstacles. Okay? Yeah? There are some moments where you don't see all these vectors, okay? Why is that? Well, that happens when there are no readings that match our filter, yeah? So remember that we are filtering detections which are away more than 60 centimeters from the robot, yeah? So if there is no reading, no laser reading closer than this, then the vectors are not computed, and the robot just keeps moving forward, yeah? There we go. Now we have the robot behind that table. See, so now we just move forward, because there are no detections being, now there is a detection here, yeah? But if there are no laser readings close enough to the robot, as you can see right now, it's going to keep moving forward, yeah? Until there are some readings which get inside the range of 60 centimeters, so then the repulsion vector is going to be computed, and it's going to start modifying the trajectory of the robot, yeah? So let me know, have you been able to, are you testing this program there in your projects? Yes, no? Are you trying this? Is it working for you? Also? I don't know what's going on here. Many messages. My robot is stuck at a wall, not moving yet. It's trying multiple vectors. Well, sometimes it might get stuck somewhere, okay? Mine is working good now, but in some cases, maybe it might get stuck in a wall or something, okay? There are some cases, like one of you was saying before, where this algorithm can fail. Yeah, it's not perfect, 100% perfect. Code running on my Roomba? Well, so Gilbert, you are running this on a Roomba? Am I understanding that correctly? Yes, okay, I can see everybody says that it is working. You can ignore the error of Qualcomm build. See, so I also have this STDR. This is a warning, it's not an error, it's a warning and you can ignore it, okay? So don't worry about that. Yeah, our robot is here still on its own adventure. Let's leave it, let's see where it ends up. Maybe it ends up outside the office, we'll see. running on a real robot here already. Okay, that's amazing, Gilbert. Subhajit has to leave. Okay, bye-bye. You are going to miss the best part, which is coming now, Subhajit. I'm sorry for you, but you can see it later. So now what we are going to do is to, okay, very cool. We can see that in the simulation it's working, Alberto, very well. But actually, I think that robot is going to end up outside the office. So this robot doesn't want to work, it seems like. See, so here it's failing because it's not detecting the code for some reason. Probably the physics of the simulation are not properly showing the... yeah, because it's only detecting the legs of the coach. You can see here the legs. But the body, it's not, the laser is not detecting the body. So it's not actually seeing that there is a coach here. See? So this is a problem that we can see, a real problem. And why is this? Well, because probably the laser is underneath the coach. So it's not able to detect it. Yeah? Okay, so let's get enough of working with the simulation, and let's get to test this in the real robot. Yeah, this is what we all want to do, and where things get actually real. So Gilbert has already done that in a Roomba, but we are going to do that in our own Limo robot. So we have a Limo robot here in our office in a lab that we have created in just 10 minutes. Yeah. So there is a very interesting thing about these robots, about Limo robots, that they come already. When you buy one of these, they are very, very easy to connect to the construct. You can have them connected to the construct and connect to them from a project in a setup that is going to take you 10 minutes at most, okay? And we have already done this. And what I'm going to do right now is to connect to it. Yeah, you are going to see it in a moment. So how do I connect to a real robot? Very easy. You have to come here to the this alien-like button that we have here in the bottom bar, which says connect to your robot. So I'm going to open this, and here I have mine set up already, which is the Limo PRO. And then all I have to do is to click on connect. Okay, I wait a few seconds, and now I'm going to be connected. When this finishes, I'm going to be connected to the real Limo robot that I have here in an office. Also, we have set up a camera so that you can see it here. There we go. Yeah, simulation, we can close it already, gazebo. Here I'm going to see the camera. It's taking some seconds to load, but it will eventually, it's retrying. Let's wait a few seconds. But yeah, whenever you connect to a lab, then the camera automatically shows up, which is this case, okay? Then meanwhile the camera loads, there is one thing that I need to do, okay? So let me, this, unfortunately, you are not going to be able to test it, okay? This part, only I can test it, okay? But you can see what, how I do it, all right? Then I'm going to do one thing, which is to do a very slight modification in the code, okay? So let me go to the code, and I'm going to show you where I touch and why, yeah? So basically I'm going to touch two things. I'm going to reduce a little bit the attraction vector here, yeah? So I'm going to comment this line where the attraction vector is 30, and I'm going to modify it to, let me see if I can, I need to change Spanish, there we go. Okay, so I am reducing a little bit the attraction vector. And also down here, I am reducing a lot the speed, yeah? So here I have some factors in order to reduce both the linear and the angular velocities. But for the actual robot, the velocities are much higher, right? So I need to reduce them more. Yeah, so here I am reducing much more the velocities. Also because in the real robot, I don't want to move it so fast. just in case something goes wrong. So I am reducing a lot the velocities here. All right? Somebody tagged me. Refresh the camera. Has the camera loaded? Let me refresh here. There we go. So here we have the environment. Yeah, so this is a room that we have in our office. Actually, it's here at my side. And yeah, this is an environment with some obstacles around. And here you can see in the middle the Limo robot. Yeah, with the eyes here, which are actually moving a little bit. It's like saying hello to all of us, right? Okay, then, all right, so now that I have done these modifications, this is something very typical, okay? So in many cases, when you move to the simulation to the real robot, you are going to have to do some small adjustments, okay? If your simulation is very well done and the robot is very similar to the real robot, which is what you should aim for, then the modifications are going to be minimal, okay? Which is this case. Yeah, here I'm just doing very, very small modifications for adjusting the simulated environment to the real environment, yeah? This is known as the real factor gap, okay? Then what I'm going to do here is I'm going to do two things. First of all, I'm going to go to my workspace and compile, because I have modified the code, so I need to recompile, right? Then meanwhile, I'm also going to open RVs, because I want to visualize what's going on in RVs, like I was doing before. Yeah, to be able to visualize all the vectors and everything. And then here I'm going to load a predefined file that I have. Saved here, the wandering configuration. There we go. Okay, so this is the real robot. These frames represent where the robot is right now, and all these colors that you can see here, you can guess that these are their laser readings, right? All these colors here. And it makes sense. If you can see, the robot is looking here forward, and right in front here, we can see the robot being detected. Yeah, this robot here is being detected right here. And then here we have the walls, right? All these walls here. Yeah? Okay, then let's go back here. Let's source. And now we are going to run our code again in the real robot. ROS2 run, Limo, what was the command? Let me get it from the notebook. I don't remember. Here it is. Okay, but before executing it, let me organize this a little bit so that I can properly see what's going on. So let me put the camera here, maybe, in the right side, so that we can see it better. Let me put it here. Then here I'm going to leave, let me put this also here, so that we can also have a look at RVs. And finally, the terminal, I'm going to make it smaller and put it here, so that it doesn't take much space, okay? So here we are going to be able to visualize RVs with the vectors that are being generated in real time, attraction vector, repulsion vector, and here we have the real environment, okay? So this is live. This is a camera that is, what you are seeing here is live. So as soon as I execute the program, the robot is going to start moving, right? So let me do that right now. There we go. Okay, so the robot starts moving forward, and you can see here the vectors already being generated, yeah? Here the vector is telling the robot to rotate to the right. It's detecting some obstacles there and say, no, go to the right. It goes. It keeps moving forward now until it finds this wall, and then it's going to start rotating to the right, as you can see. Here it's going to find this robot. It also rotates to the other side, avoiding this robot, as you can see. Now it's doing a weird rotation. Okay, let's leave it. Let's leave it moving around a bit more. Okay, there you can see how we detected this arm here also, and then, oops, sorry, I click the pause button. Now it's going to detect also this wall, and it's starting to tell the robot to rotate, as you can see. Okay? See, now it detects this and it rotates to the other side. And basically the robot is going to continue. Now it's going to detect this robot and also it's going to try to avoid it. And yeah, basically the robot is going to keep moving. There are some endpoints where maybe it's not able to avoid something properly, but yeah, here you can see that the same code that we tested in the simulation, we move it to the real robot, and it's working. Yeah, so it's generating the vectors, and it allows the robot to avoid the different obstacles. Here it's going to move around the robot. Yeah, I think it's going to be able to move around the robot. Yeah. Okay, excellent. So I think I'm going to stop it here since we are already at 7. Then let me have a look here at the chat to see some question from you. Syntax error. Okay. This Gianta probably means that you have copied the code with using the copy tool. Okay. Either this one or maybe this one. Okay. So don't do that. Remove the code that you have. Remove everything and copy it again like this by selecting everything, copy and paste. Okay. Don't do it with the tool. Probably that's the reason. Will the ROSject, Jan is asking, will the ROSject be available after class? Yes. And not only after class, but you are going to have this ROSject forever in your account. Okay? So for the people who that you have copied the ROSject for today's class, you are going to have this forever, right? Then, let me leave here. So I'm going to leave the robot here moving around a bit, wandering, yeah? I'm going to leave it wandering a bit here. Meanwhile, I check the hopefully nothing strange is going to happen. No, I think I can trust it because as you can see, it avoids everything pretty good. So, okay, then what else? What else do we have? The video and the ROSject are going to be available. Yes, exactly. How would you compare the Limo to the Turtlebots? And how is the mechanical dependability of the Limo? You say to the Turtlebots. I mean, there are many different models of the Turtlebot. So I don't know exactly which one you mean, but for instance, if we compare it to a Turtlebot 3, this here in the video, you can see this robot that you have here, that the Limo robot is going around right now. This is a Turtlebot 3. So, as you can see, it's a much simpler version of the... Let me refresh the camera because I think it's a bit laggy right now. Will it kind of freeze it? Ah, there we go, yeah. Now it is. Yeah, so this one that you have here, this is a Turtlebot 3. So, as you can see, it has nothing to do. I mean, very different robots. The Turtlebot 3 is much more simple. It's also much more cheap, right? But, so the Limo robot has many more capabilities than a Turtlebot 3, for instance. Yeah, and even with a Turtlebot 4, it would be there. Okay, so if I have, probably if I had to pick one right now, I would go for the Limo. Okay, because something that the Limo has that not many robots have is the possibility to work with differential drive, with holonomic, with omnidirectional mode, and with Ackermann mode. This is super interesting, okay? And you have a laser data, which is always a must for navigation. You have a point cloud camera, which is also super good for doing perception things. So it's a very complete robot. And yeah, so I don't know if that more or less answers your question. Yeah, so it has also a jet sonoring for deep learning, exactly. Okay, then what I wanted to say now, before ending the class, is that this robot, the Limo robot, so it has an official cost, you can see it here at the end, It has an official cost of $3,200. Okay, this is the official price. But thanks to the Agile X people, we have an offer, a special offer for the audience of this open class, for 24 hours, okay? So you can get it by $2,000. So it's basically a discount of $1,200, okay? Only for the next 24 hours, unlimited to 5 units, okay? So the deadline for this offer is going to be tomorrow, February 29th at 22 CET. Then if you want to get one Limo PRO robot, the one that we have been working today with, by only $2,000, more than $1,000 of discount, what you have to do is to send an email before the deadline, before tomorrow at 22 CET, to this email, info@deconstructsim.com. You can write an email to this address saying, hey, I attended the open class and I want to get a Limo PRO, okay? And then the first 5 people that send this robot are going to get, that send this email, are going to be able to get one Limo PRO by 2,000, okay? So, super good offer, if you ask me. Yeah. Then from my side, I think I'm going to leave it here. I have also left here a link to our ROS2 Basics course, in case that you missed some things in this class. Everything, all the ROS2 Basics concepts are explained here. How to create publishers, subscribers, nodes, callbacks, multi-threading, everything, you have it in this course. And yeah, so that's everything from my side. Let me switch here to my screen again. Somebody has tagged me because I can see. Gilbert says, thanks for another great open class. Okay. All right. Yeah, so I'm going to leave it here then. Thanks to all of you for attending to this class, or also for participating, making your questions, providing feedback. So this makes the classes much more dynamic. So thanks to all of you. I hope that you have enjoyed the class, that you have learned something new. And yeah, I will see you in the next one. And as always, until then, keep pushing your ROS learning. Bye-bye.